Hi class, this is Dr. O'Connor. In this video I'm going to talk about atomic theory and the structure of atoms, elements and atomic number, and mass number, and isotopes and atomic mass. So let's go ahead and start with section 1. And let's talk a little bit here about the atom. The smallest and simplest particle of an element that still retains the characteristics of that element is called the atom. According to modern atomic theory, there were 4 fundamental assumptions made by an English scientist called John Dalton. And these assumptions were formed by him to explain the chemical behavior of matter. So the first assumption, all matter is composed of atoms. Atoms of a given element differ from atoms of all other elements. So in other words, a carbon atom is going to differ from a hydrogen atom. An oxygen atom is different from a helium atom, and so on. Chemical compounds consist of atoms combined in specific ratios. Only whole atoms can combine. So for example, here we have water, and that is composed of 2 hydrogen atoms and 1 oxygen atom, and yet here we have hydrogen peroxide. That's 2 hydrogens to 2 oxygen atoms. Both are different compounds. And as we see, we have whole atoms that combine. We don't have half atoms or quarter atoms that combine. Chemical reactions change only the way that atoms are combined in compounds. The atoms remained unchanged. And we'll talk more about that in a later chapter. But you can think of a chemical reaction as a rearrangement of atoms. So bonds are broken and new bonds are formed. Next, we'll talk a little bit about the structure of the atom. First, you need to know that an atom is electrically neutral. And what does that mean? It means that there are an equal number of protons and electrons. Let's talk a little bit about the protons and electrons. First, let's take a look at the mass of a proton. The mass of a proton is 1.6726 times 10 to the negative 24 grams. The mass of a neutron is very similar. It's 1.674927 times 10 to the negative 24 grams. Then let's take a look at the mass of the electron. 9.109328 times 10 to the negative 28 grams. Compared to protons and neutrons, the electron mass is negligible. Let's take a look at some sizes of atoms. So the size of an atom ranges from about 7.4 times 10 to the negative 11 meter to 5.24 times 10 to the negative 10 meters in diameter. Masses of atoms range from 1.67 times 10 to the negative 24 grams to 3.95 times 10 to the negative 22 grams. So here's an example. We're dealing with very small entities here. If I were to draw a line with a pencil, so a very fine pencil line, then the thickness of that line, so we're talking in the thickness here, okay, that would be about 3 million atoms. And again, that'd be a very fine pencil line, not this huge one that I drew. Okay, so let's talk a little bit about the nucleus. The nucleus of the atom is very dense. It contains most of the mass of the atom, so therefore it contains the protons and the neutrons. Okay, so we have both a nuclear region where the protons and neutrons reside, and again, that's most of the mass of the atom. And then we have an extranuclear region And that's mostly empty volume where the electrons reside. So here we take a look at this drawing right here, and this represents the nucleus, and this blue part here represents the mostly empty volume that contains the electrons. So here this diameter is about 10 to the negative 10 meters. So we see that the nucleus is very small compared to the extranuclear region. So what we have is positively charged protons and neutral neutrons in the nucleus. Again, it's the nucleus that contains most of the mass of the atom. Let's go up here. We call the protons, neutrons, and electrons subatomic particles. So a proton is a positively charged subatomic particle, has a mass of 1.672600 times 10 to the negative 24 grams, and it carries a positive 1 charge. A neutron, on the other hand, is electrically neutral. Its mass is almost the same as a proton, and it's electrically neutral. By the way, sometimes you'll see the symbol for the proton written like so, symbol for the neutron like this, and then we have the electron. It's a negatively charged subatomic particle. It carries a charge of a negative 1, and sometimes you'll see the symbol written like so, lowercase e with that negative sign. So let's talk a little bit about atomic masses. And when you think about it, when you think about the size of an atom and then the size of the protons, the neutrons, and the electrons that make up the atom, well, think about it. The atomic masses that would be measured in grams are too small. We can't measure something that small in the lab. So what we do is we express the atomic masses using a relative mass scale. It turns out that we assign one atom a mass, and all the other atoms of the elements on the periodic table are going to be measured relative to that. The atom is what we call carbon-12. Carbon-12 contains 6 protons and 6 neutrons, and that is assigned a mass of 12 atomic units. Atomic mass units are represented by AMU, so atomic mass units. So, because the carbon-12 atom has 6 protons and 6 neutrons, and because the mass of a proton and a neutron, because those masses are almost identical, we say that one atomic mass unit is 1/12 the mass of a carbon atom. Remember, you have 6 protons plus 6 neutrons equals 12. So one atomic mass unit is 1/12 the mass of a carbon atom. And both protons and neutrons have a mass of 1 atomic mass unit. So it turns out that 1 atomic mass unit has a mass of 1.66 times 10 to the negative 24 grams. So you'll want to remember this, okay? So that means a proton, a neutron, has a mass of 1.66 times 10 to the negative 24 grams, which is equal to 1 atomic mass unit. So we could easily find out the mass in grams of one atom of carbon. We know that carbon has 6 protons, 6 neutrons, so that would be 12 atomic mass units. 12 times this number here would give us the mass in grams of one carbon atom. So as I said, all of the other elements' atoms are measured relative to carbon-12. So it turns out a hydrogen atom is 1/12 the mass of carbon, or it's 1 atomic mass unit. Magnesium is twice the mass of carbon, or 24 atomic mass units. Lithium is 1/2 the mass of carbon, or 6 atomic mass units. Let's go back to the periodic table here. And this is our periodic table. And a little bit later, we'll talk about these numbers that are above the elemental symbol. But let's take a look at this number here. This number here corresponds to atomic mass. So for example, one atom of, let's do carbon. So one atom of carbon would have a mass of 12.011 atomic mass units. One atom of oxygen would have a mass of 15.9994 atomic mass units. That is the atomic mass. All right, these are atomic masses. A little bit later, we'll see how those relate to the mole and grams. So here's a problem for us. We're being asked how many atoms are in a piece of gold that has a mass of 26.4 grams. That's what we measure on the scale. Here we're told the mass of one atom of gold is 197 atomic mass units. Oh, we can set up an equivalence here. So here we're given a mass. So our given is 26.4 grams. And what are we being asked for? We're being asked for how many atoms. So our desired unit here is number of atoms. So we need to go from grams to atoms. Can we do that? Well, we can go from grams to atomic mass units, and then from atomic mass units to the number of atoms. Here I have my roadmap. So how do I go from grams to atomic mass units? Well, what do I know? I know that 1.66 times 10 to the negative 24 grams equals 1 atomic mass unit. So that's good. So how do I go from atomic mass units to atom? I know that from the problem, 197 atomic mass units is equal to 1 gold atom. This is the symbol for gold. So I'm all set to go. I can make 2 conversion factors for each one of these equivalences. So I start off with what I'm given, 26.4 grams. I want to cancel out grams and end up in atomic mass units. So I use this here. I'll put this in the denominator. And this is 1 atomic mass unit. So grams cancel out. And if I were to stop right here, I'd have the number of atomic mass units. And I know that 197 atomic mass units. Remember, I want atomic mass units to cancel. So I'm left with atoms. I get 8.07 times 10 to the 22 gold atoms. That's a lot of atoms. In fact, that is this many atoms. Okay? So what I was able to do here was, again, I was able to use this conversion factor and then this equivalence. I was able to come up with my conversion factors. Again, the whole point is you want to cancel these units out. I wanted to cancel grams to get to atomic mass units. And then I wanted to cancel atomic mass units to get to the number of atoms. Practice those problems. There are quite a few at the end of the chapter and also in the practice problems that I provided for you. We know that the nucleus contains the protons and the neutrons, and then the extranuclear region is where the electrons reside. So it turns out that atomic structure happens to be the result of the interaction between forces, both attractive and repulsive. Well, we know that opposite charges attract, like charges repel. So let's think about it. We have a positively charged nucleus, and we have negatively charged electrons. So those negatively charged electrons are attracted to that positively charged nucleus, and that's why the electrons stay close to the nucleus, because of that attraction. Now, as I said before, like charges repel each other. So the negatively charged electrons will try to be as far away from one another as they can. And this is why the extranuclear region is so large, because those electrons repel one another. So we have attractions between protons and electrons, repulsions between electrons. Now, protons also repel one another, but we're talking about very small distances between those protons in that very small nucleus. And there is a unique force called the nuclear strong force that we're not going to go into here. So just take my word for it that those protons are very happy in that nucleus. So now let's talk about atomic number. And the atomic number is represented by a capital Z, and this corresponds to the number of protons contained in the nucleus of an atom. It also corresponds to the number of electrons in an atom. The reason why is, if we're talking about a neutral atom, the number of electrons must equal the number of protons. In other words, there has to be a zero net charge. So let's take a look at the periodic table again. And here it is. So what we have, this number here that's above the elemental symbol, that is the atomic number. That is Z. So lithium has an atomic number of 3. That means it has 3 protons in its nucleus, and a neutral lithium atom will have 3 electrons. Here we have aluminum, and aluminum has Z equal to 13, so it contains 13 protons, and a neutral aluminum atom will also contain 13 electrons. The atomic number is important because it's the atomic number, or Z if you will, that identifies an element. If I say identify the element with Z equal to 29, you go to the periodic table, look up the atomic number, and that corresponds to copper. If you still have your periodic table in front of you, you'll see that for Z equal to 1, the element is hydrogen. For Z equal to 20, the element is calcium. Notice that on the periodic table, the elements are ordered by atomic number when we read from left to right. Again, as I said, Z gives us the identity of the element. Now there's another number called the mass number that's represented by a uppercase A. And that gives us the sum of protons and neutrons in an atom. So A is always a whole number. I will tell you right now, the atomic masses on the periodic table do not correspond to A. Okay? So let's take a look here. We have hydrogen. It has a hydrogen atom with 0 neutrons and 1 proton. A is equal to 1. If a nitrogen atom has 7 neutrons and 7 protons, the mass number is 14. For a sodium atom with 11 protons and 12 neutrons, A is equal to 23. So it turns out that many atoms contain more neutrons than protons, and we cannot determine the number of neutrons just by looking at the periodic table and those atomic masses. We cannot do it. Remember what I said. A is always a whole number. Why? Because it's the sum of protons and neutrons. We don't have half neutrons or half protons. Okay, let's take a look at an example here. We have 2 examples, or 2 problems. How many protons, electrons, and neutrons are there in an atom with atomic number Z equal to 13 and mass number A equal to 27? what is the identity of the element? Well, first, the only number here that's going to identify the element is Z. So I'm going to go to my periodic table and look for Z equal to 13. And let's see, right here it is. It's aluminum. So let's go back here. The identity of the element is aluminum. And they're asking how many protons, electrons, and neutrons. Well, we know that there are, Z is 13, so there are 13 protons. It's a neutral atom, so there are 13 electrons. And how many neutrons? Remember, A is the sum of the neutrons and the protons. So we have 27 minus 13. So what we have is 14 neutrons. Okay? So if you're not given A, you cannot determine the number of neutrons. You cannot determine that from the periodic table. Here's one here. An atom has 19 protons and A is 39. How many electrons and neutrons? What is the element? Let's go see what the element is first. Oops, I forgot what Z is. Well, we have 19 protons, so Z is 19. So let's go ahead and look that up on our periodic table. And what do we have? So Z equals 19 corresponds to potassium. So let's go back here. So our element is potassium, and it has, we already know it has 19 protons, therefore 19 electrons. And how many neutrons? That's going to be 39 minus 19, and that's going to be 20 neutrons. So we have 19 protons, 19 electrons, and 20 neutrons. Now, we're going to talk about isotopes. And the definition is two atoms that have the same number of protons, in other words, the same element. Remember, it's the number of protons, or Z, that identifies the element. So it's two atoms, or we should say two or more atoms, with the same number of protons, but different numbers of neutrons. Okay, so here's an example right here. I have this figure. And here we have 6 protons in the nucleus. This one also has 6 protons in the nucleus. This one has 4 neutrons, and this one has 6 neutrons. So this is a pair of isotopes. So an isotope then, isotopes have identical atomic numbers, or Z, but different mass numbers, A. Turns out that isotopes have identical chemical properties. They can differ slightly in physical properties, something called half-life, which we'll probably talk about later. And most of the naturally occurring elements are a mixture of isotopes. So for example, hydrogen has 3 isotopes. What that means is, if I collect a sample of hydrogen, no matter where I collect it from on this earth, it is going to contain these 3 isotopes. That sample will contain protium, deuterium, and tritium. So protium has 1 proton, 0 neutrons, therefore A is 1. And it turns out that for any sample of hydrogen, 99.985% is going to be due to protium. Deuterium has 1 proton and 1 neutron. That means A is 2. And for any sample of hydrogen, 0.015% of that is going to be due to deuterium. And then there's tritium. 1 proton, 2 neutrons, A is equal to 3. And as you can see here, very, very small percentage of a hydrogen sample is due to tritium. Before we go any further than that, let's go ahead and take a look at isotopic symbols. So this here is the isotopic symbol for tritium. Okay? So we write the element symbol, and then the superscript in the upper left-hand side is the mass number, so that is A. And then the atomic number, Z, is in the lower left-hand corner. So this is an isotopic symbol. So for example, here it says write an isotopic symbol for uranium-235. Anytime you see this, or I might say carbon-12, this is the mass number A. So I start with my element symbol, and I know that A goes up here, but now I have to go to the periodic table to look up Z. So let's go ahead and do that. So for 235, for uranium, okay, here it is, Z is equal to 92. So let's go ahead and write that. So this would be the isotopic symbol for uranium-235. Here they want isotopic symbols for carbon-12 and carbon-13. So here's the mass number, and we know Z for carbon is 6. And then for carbon-13, mass number, and Z is 6. So these are the isotopic symbols for carbon-12 and carbon-13. Okay? Turns out, as I said, many of the naturally occurring elements are a mixture of isotopes. So for example, oxygen contains 99.759% oxygen 16, 0.037% oxygen 17, and 0.204% oxygen 18. So this is where we define the atomic mass. This is the weighted average atomic mass of an element's atoms. All of the naturally occurring isotopes of that particular element are included in determining the atomic mass. Okay, your book uses weight, so I like to use the term mass. So, for example, the atomic mass of oxygen, which is shown on the periodic table, is 15.9994. Okay, that is determined by these three naturally occurring isotopes. Okay, so how do we determine an atomic mass? Well, what we do is we sum the isotopic abundance multiplied by the isotopic mass for each of the isotopes. We sum those together. That's what this symbol means. And that will give us the atomic mass of the element. So that's how the atomic masses of all the elements are found. Let's go ahead and take a look at what we have here. We're told that naturally occurring silicon, which makes up 25% of the Earth's crust, consists of 3 isotopes. 92.23% is silicon-28, and here's its atomic mass. 4.67% is silicon-29, and here is the isotopic mass for that. And 3.1% is silicon-30. Let me rewrite that. I forgot to put the superscript there. And here is the isotopic mass for silicon-30. Wants us to calculate the atomic mass of silicon. Well, again, I have to take each isotopic abundance, multiply by the isotopic mass, and then sum them together. So let's go ahead and do that. Okay. Now, obviously, this 4.67% and the 92.23%, 3.1%, these are what we call percent abundances. What we want is the fractional abundance. All right, let me put that up here. So fractional abundance. How do we get the fraction from the percent? We just divide it by 100. So let's start off here with silicon-28. So we have 92.23%, and the fractional abundance would be 92.23 divided by 100. So that would be 0.9223. We multiply that by the isotopic mass, which is 27.99. 0.976927 atomic mass units. And then let's do silicon 29. And silicon 29, or it has a percent abundance of 4.67%. So the fractional abundance would be 0.0467. We'll multiply that by the isotopic mass. That's 28.976495 atomic mass units. And then we'll do the same thing for silicon 30 and 3.10%, but we want the fractional abundance. It's going to be 0.0310. We'll multiply that by the isotopic mass, which is 29.973770 atomic mass units. So let's go ahead and multiply each one of these. This first one, I get 25.80311977 atomic mass units. Let me do the second one, 0.0467 times 28.976495. I get 1.3532023 atomic mass units. And then let's do this one, 0.031 times 29.97377, and I get 0.9291867 atomic mass units. So what I'm going to do is now add these. Okay, so we've taken the fractional abundance multiplied by the isotopic mass for each one, and then we sum them together, just like this equation tells us. Before we do that, what we have to do is figure out our significant figures. So here we have 4, and here we have 2, 3, 4, 5, 6, 7, 8. So this answer here can only have 4 significant figures. Let's take a look at this one. Here we have 3 significant figures. Here we have 1, 2, 3, 4, 5, 6, 7, 8. So we can only have 3 significant figures here. And then here we have 3 sig figs. Okay, so only 3 here. Okay, so let's go ahead and add these. So here I get 28.0855089 atomic mass units. And let's see what we have here. Now we're adding, so I have to look at the digits beyond the decimal point. Here I can have 2, here I can have 2, and here 3. So we can only have 2 digits after the decimal point. So this would be 28.08 atomic mass units. Some of you might round that up to 28.09 atomic mass units. That's fine. You're dropping a 5. Usually if there's an even number left, I leave it. If it's an odd number, I round up. But this is how you find an atomic mass or an atomic weight. On an exam, I won't give you the element name. I would give you something rather than telling you, well, it's silicon, I'd probably say element X. But there will be one of these on the exam. I'd give you, of course, either the percent or the fractional abundance. You have to know which ones to use. And I would give you the isotopic masses. But again, I wouldn't give you the element. I'd probably just use an X or a Z. Let's just do this one final problem here. Here they want us to identify the element X in the following. They want the atomic number, the mass number, number of protons, number of electrons, and number of neutrons. Obviously, this is Z, this is A, so Z gives me the identity of the element. Let's go to the periodic table, and Z equal to 12 is magnesium. So let's go back up here. We know that the element is magnesium, and it wants the atomic number, so Z is 12. It wants the mass number, that's A, that's 21. That's this one here. Mass number is always here on top, and Z is always below the mass number. Wants to know the number of protons, so that corresponds to Z, so 12 protons. Neutral atom then would have the same number of electrons, and then the number of neutrons would be A minus Z, so 21 minus 12, and that would be 9 neutrons. Okay, that's it for this part of the video. The next video we'll talk about the periodic table, and I'll talk about some of the different groups on the periodic table, and then the third video will be on electronic structure of atoms, electron configurations, and so on. So everybody have a great evening. If you have any questions, please contact me.